All right, today we're going to dive into Salmonella's incredible and honestly pretty clever two-phase strategy for infecting a host cell. Think of it like a classic smash and grab. First, there's the violent but really well-planned break-in. And then there's the long-term survival and replication, once it's already deep inside enemy territory.
So you might be wondering, how on earth does a single bacterium pull off that dramatic first phase? In this explainer, we're going to focus on exactly that. We're going to unpack how Salmonella executes what is, for all intents and purposes, a molecular heist, forcing its way into a cell that really has no intention of letting it in.
Now, to pull off a heist of this magnitude, Salmonella doesn't just wing it. Nope, it comes prepared. It's equipped with this highly specialized set of genetic tools, and they're all conveniently organized in one specific region of its chromosome. These genetic toolkits are called Salmonella pathogenicity islands, or just SPIs for short. And you can kind of think of them as weapon caches that the bacterium has, picked up from other microbes over millions of years of evolution. And for the mission we're talking about today, the break-in, we are laser-focused on the most important one, SPI-1. And this is the key. SPI-1 isn't just one single tool, it's the entire blueprint. It has the complete set of schematics and all the instructions the bacterium needs to build this incredibly complex machine for forcing its way into a host cell. So, what does this amazing machinery actually look like? Well, the centerpiece of the whole SPI-1 toolkit is this just stunning piece of nanoengineering. It's called the Type 3 Secretion System, or T3SS1. And its function is every bit as elegant as its design. The moment it makes contact with a host cell, the T3SS1 literally self-assembles into a structure that acts just like a microscopic syringe. It builds a direct channel, pierces the host cell membrane, and gets ready to inject its payload right into the cell's cytoplasm. Okay, so we've got this molecular syringe ready to go. The big question is, what is it injecting? It's not a poison or a toxin in the way you might think. Instead, it injects this really carefully crafted cocktail of saboteurs. We call them effector proteins. And these are the agents that are going to carry out the heist from the inside. So let's meet the key players in this operation. You've got proteins like SopE, SopE2, and SopB. These are the masterminds, right? Their job is to hotwire the cell's own internal command and control systems. At the same time, you've got another protein, SipA, which acts more like an on-site foreman, directly getting its hands dirty and manipulating the cell's structural beams to make sure the plan goes off perfectly. So here's the play-by-play. Once they're injected, these SOP proteins, they immediately go to work. They find and they flip on the host's own regulatory switches, these things called Rho GTPases. Now, these are the molecules that normally keep the cell's internal scaffolding, its actin cytoskeleton, all nice and orderly. But by flipping these switches, Salmonella unleashes absolute chaos. It causes this massive, uncontrolled explosion of actin filament growth right there at the point of contact. We put together these custom deep dives just for you. So if you're finding this useful, a quick like and subscribe goes a long way. All right, let's get back to the heist. Okay, so we have this massive, chaotic explosion of actin inside the cell. But here's the brilliant part. It's not random. Not at all. Salmonella is creating all this internal disruption for a very specific and, frankly, genius purpose. The whole point of all this internal mayhem is to force the host cell to do something completely unnatural, something it would never, ever do on its own. The result of all that actin polymerization is, well, it's pretty spectacular. It forces the cell's own membrane to erupt into these enormous wave-like extensions. We call them membrane ruffles, and they look like these giant arms reaching out from the cell, and they have one single target, the Salmonella bacterium just waiting outside. This powerful invasion strategy has a name. It's called Salmonella-induced macropinocytosis. The key word there is induced. The bacterium triggers the cell to do this. It's not a quiet, gentle entry. It's a forced engulfment where the bacterium tricks the cell into reaching out, grabbing it, and basically swallowing it whole. And it's really important to get this. This trigger mechanism is fundamentally different from other bacterial strategies. So, for example, a bacterium like Listeria uses what's called a zipper mechanism. It's a much more subtle, adhesion-based process where the cell membrane kind of gradually and neatly closes around it. Salmonella's approach, on the other hand, is loud, it's violent, and it's a totally disruptive forced entry. So, there you have it.
The heist is a success. You can imagine the alarms are blaring inside the cell, but it doesn't matter. The bacterium has breached the outer defenses and is now on the inside. So, what's the immediate result of this invasion? Well, the bacterium is now safely enclosed inside its very own getaway vehicle, a membrane-bound bubble that it forced the cell to create. This is known as the Salmonella-containing vacuole, or SCV. But getting inside is really only half the battle. From within this early vacuole, Salmonella is now perfectly positioned to begin phase 2 of its attack, transforming this temporary holding cell into a protected fortress where it can survive and even multiply. And that whole complex process, well, that is the focus of our very next explainer. All right, continuing our discussion on Salmonella's bag of tricks, we're moving on to SPI2 and intracellular survival. So the bacteria is now inside the host cell, trapped in a little bubble called the Salmonella-containing vacuole. This should be the end of the road for it, but it's not. Let's explore the absolutely brilliant strategy Salmonella uses to turn this prison into a 5-star hotel. So yeah, this is the big question, isn't it? It's been captured, it's been enclosed by the host cell. So how does it survive? How does it possibly turn what's designed to be a death trap into its own personal stronghold? This whole battle plays out on a microscopic stage, and that stage is called the Salmonella-containing vacuole, or SCV for short. This is where the bacterium's fate is going to be decided. See, the host cell's plan is actually pretty simple. Trap Salmonella in the SCV and then fuse it with lysosomes, the cell's demolition crew, to just completely obliterate the invader. But Salmonella has other plans. It's about to pull off this incredible act of cellular hijacking, turning what should be death row into a safe house. And this really lays out the conflict perfectly. On one hand, the host cell is actively trying to deliver its payload of destructive enzymes to that SCV. But on the other hand, Salmonella is working just as hard to stop that from happening, remodeling the vacuoles so it can multiply safely inside. It's a true molecular arms race. So how does Salmonella actually pull this off? Well, it has a secret weapon. It's called Salmonella Pathogenicity Island 2, or SPI2. Think of this as the bacterium's master key, a whole genetic toolkit that's designed specifically to hijack the host cell's machinery from the inside. So once it's safely inside that SCV, Salmonella flicks a switch and activates its SPI2 system. This system puts together a molecular syringe, the T3SS2, which is just incredible. It acts like a needle that pokes out from inside the vacuole's membrane. And through this syringe, Salmonella injects a cocktail of proteins directly into the host cell's cytoplasm, letting it basically rewire the cell's controls. Okay, so how does this whole system work? Well, it's basically a 3-step heist. First, Salmonella injects proteins to change the molecular address labels on the outside of its vacuole. This makes the vacuole invisible to the lysosomes. Second, it actively blocks the pathways that lysosomes would use to find it anyway. And third, in a really stunning move, it reroutes the cell's entire internal supply chain, redirecting vesicles full of nutrients to its own vacuole. So it stops the bombs from arriving and orders itself a pizza instead. But this isn't just about survival, it's about conquest. By turning host cells into factories, Salmonella is building an army. And once that army gets big enough, it's ready to break out and invade the rest of the body. This is where a localized gut infection morphs into a much more dangerous systemic problem: bacteremia, or bacteria in the bloodstream. By converting host cells, and especially immune cells like macrophages, into these little protected incubators, Salmonella can just replicate in huge numbers. This allows it to break out of the intestinal lining, travel through the lymphatic system, and get access to the bloodstream, transforming what was a local gut infection into a systemic disease. Now, while bacteremia might happen in about 5% of otherwise healthy people, that risk just skyrockets in patients whose defenses are already weakened. And this is where understanding all this pathophysiology becomes absolutely critical for us in the clinic. A 25-fold increased risk. Just let that sink in for a minute. This is not a small jump. It's a massive leap in vulnerability. It tells you that for certain patients, the body's normal defenses against Salmonella are fundamentally broken, and that can turn a manageable infection into a life-threatening one. And this slide explains exactly why. In patients with sickle cell disease, the spleen, which is supposed to be the body's main blood filter, just doesn't work right. It can't clear the Salmonella out. And in patients with HIV, the macrophages themselves are impaired. So the very cells that Salmonella loves to hide in are even worse at killing it. It's the perfect storm for an overwhelming infection. And once Salmonella is just circulating in the blood, it can set up shop pretty much anywhere. This is the real danger of bacteremia. It's not just a gut problem anymore. It's a potential infection of the bones, the heart, the brain. Anywhere the blood flows, Salmonella can go. And some of the most serious consequences are right here. Salmonella has the scary ability to infect damaged blood vessels, causing life-threatening infections of the aorta. It can cause meningitis in newborns, and, critically, it can infect bone, which leads to osteomyelitis. And this is a clinical pearl you absolutely have to remember. In patients with sickle cell disease, Salmonella is the #1 cause of bone infections. It's even more common than Staph aureus, which is usually the main culprit. And this is a direct result of that impaired spleen we talked about. It lets the bacteria hang around in the blood long enough to seed into areas of bone that are already damaged by sickle cell crises. Okay, let's bring this all home and tie it together with the key points to remember. So, the bottom line is this. Salmonella is not a passive victim inside the cell. It uses its SPI2 secretion system to actively remodel its vacuole, blocking its own destruction and ordering in nutrients. This intracellular survival is the launch pad for systemic infection. And clinically, you have to have a very high index of suspicion for severe, invasive Salmonella disease, especially bacteremia and osteomyelitis in any patient with HIV or sickle cell disease. And that really is the inside story of how Salmonella turns a death sentence into a new lease on life. If you found this explainer helpful, please like and subscribe for more custom medical videos made just for you. Now, moving on to the next segment.